Hello everyone and welcome to my channel. We continue with some short problems in classical mechanics at the undergraduate level. Today I would like to bring you the concept of Galileo invariance, which was a key concept in the 17th century for the development of Newton's laws and for Newton and Galileo themselves, and also introduce the concept of inertial frames of reference and their importance in physics. The exercise consists in demonstrating that Coulomb force is invariant under a Galileo transformation. A Coulomb force is the interaction between two physical objects and that depends on their separation distance. Here we got a usual reference frame O, X, Y, Z. Imagine two particles in space. The position, let's say, of particle labeled I is simply R sub I. And on the same way, the position of particle J is R sub J. By sum of vectors, this red vector here connecting both particles is simply R sub I minus R sub J. So the force that the particle I experiences due to the presence of the particle J has this mathematical expression, where K is a constant that can be positive, meaning in this case that the force is proportional to the vector R sub I minus R sub J that points in this direction, and as a consequence the particle I would move away from particle J. So here we would have a repulsive force. If the constant K is negative on the other hand, the force on the I particle would be antiparallel to R sub I minus R sub J, and therefore the particle would move towards particle J. So we will have an attractive force here. I would like to point out here that the concept we want to focus on is the distance between the two physical objects. But the idea is completely analogous for a system of particles, for example, where we would have to sum all the 2 by 2 interactions among the particles, or in the continuous where we take 2 by 2 interactions between two differential elements of the two continuous bodies and then integrate over the two domains of region of the two bodies. So as said, we just focus on that we are dealing with a distance interaction that depends on the inverse square distance. For simplicity, just consider two particles with positions r sub I and r sub j refer to a fixed reference system O, X, Y, Z. Refer to a reference O prime, X prime, Y prime, Z prime. The positions of these two particles will be simply r sub I, r prime sub I, and r prime sub j. But what it is key here is that the distance between both particles given by the vector r prime sub I minus r prime sub j between both particles would remain the same. The distance vector, therefore, would lead to the same force measured from both reference systems. Moreover, the vector connecting particle j and particle I remains the same no matter where we put the reference frame. Though this might be obvious from our common experience, the distance between two objects remains the same no matter where we look from. This is not always obvious and is not true in special relativity, for example. But for now, we just stay at the obvious with classical mechanics. To put on perspective of what comes later, let's define what is an inertial frame. Inertial frames are those stationary or uniformly moving frames of reference. All frames of reference with zero acceleration are in a state of constant rectilinear motion, straight line motion with respect to one another. By contrast, an inertial reference frame has no zero acceleration. Consider a system O, X, Y, Z fixed, another system O prime, X prime, I prime, Z prime that moves with constant velocity Vt from the first one. Important is that this prime system does not rotate because a rotation would introduce an acceleration and therefore the system would not be inertial. A single particle in space has position r referred to system O, X, Y, Z and position vector r prime referred to system O prime, X prime, Y prime, Z prime. By the sum of vectors rule, it is very easy to see that the two position vectors relate to each other by r equals r prime plus vt. This is known as a Galileo transformation, but this is completely analogous to this situation here. Imagine the system, it is the system OXYZ that moves from the left, from the system with primes. The situation is completely analogous and the same equation remains. R prime equals R minus Vt. It is the same Galileo transformation, but instead of measuring from system OXYZ, we measure from system O prime, X prime, Y prime, Z prime. Therefore, two inertial observers see each other moving with constant motion. Poorly, none of them can tell which is at rest or which one is in motion. Then, on the 17th century, the great Galileo Galilei comes along, and in his dialogue concerning the two chief world systems in 1632, states that the laws of motion must be the same in all reference frames. He stated this using the example of a ship traveling at constant velocity on a calm sea. Any observer would not be able to tell whether the ship is moving and the sea is stationary, or the ship is stationary and the sea moving. Going back to what the exercise asks for, that Coulomb law is invariant under a Galileo transformation, consider Alice here in an inertial frame OXYZ. Alice measures position vectors r sub I and r sub j for the two particles, and r sub I minus r sub j for the distance vector between both particles, and consider both here traveling on O prime, X prime, Y prime, Z prime system with constant velocity. He measures r prime sub I and r prime sub j for the particles. The Coulomb force that Alice measures is this, as we shown before. But r sub I, by the rule of summing vectors we've got here in the drawing, is just r prime sub I plus Vt, and r sub j is r prime sub j plus Vt. The terms Vt cancel out, and we finally get the same expression with primes, that is the force referred to O prime, X prime, Y prime, Z prime, where Bob is. Therefore, inertials Alice and Bob agree on the same interaction. This was expected as we saw before. The Coulomb law is the same referred to any reference system as long as the distance between particles remains the same. Therefore, we prove the exercise. The Coulomb law is invariant under a Galileo transformation. Though this might seem obvious, it does not apply in special relativity, where velocities between inertial systems are very high, meaning very high, they approach the speed of light, and where funny and counterintuitive phenomena appear, like the length contraction or time dilation. But for the moment, we stay with classical mechanics. So inertial frames are those related via constant velocity. Galileo concludes that two inertial observers should measure the same laws of motion. And the important here is that he concluded this before a very important guy showed up. And this great important sir is no other than, ladies and gentlemen, the great Isaac Newton, who in the late 17th century put quantitatively this concept in one of the most important equations in human history. Force equals mass multiplied by acceleration. This is Newton's second law. Force is the cause of motion. Acceleration is the effect, therefore. An object given a force experiences an acceleration, and an accelerated object is therefore subjected to a force. The merit of Galileo is that he concluded that two inertial observers will experience the same effect on motion before Newton brought in his equation. And this is what we are going to prove now with the help of Newton's second law. Consider Alice and Bob again. Let's work out the equation of motion for particle I subjected to the Coulomb force for both reference systems. Alice sees the particle I subjected to force F sub I and an acceleration that is simply the second derivative in time of the vector r sub I of the I particle referred to O, X, Y, Z. And Bob measures particle I position subjected to force r prime sub I, which we showed before equals f sub I, the same as Alice. And an acceleration given by the second derivative in time of the position vector r prime sub I referred to O prime, X prime, Y prime, Z prime. But r prime sub I is simply r sub I minus vt under a Galileo transformation. And since O prime, X prime, Y prime, Z prime is an inertial frame, v is constant. And therefore, its second derivative in time is zero, and Bob also sees an acceleration for the I particle given by the second derivative of r sub r, except the mass, of course. Particle has mass m, the same as Alice sees. So as we see using Newton's second law, the two inertial observers, Alice and Bob, measure the same equations of motion. And here is the proof. The equations of motion are the same in all inertial reference frames. Therefore, two inertial observers should measure the same physics. I would like to end the video with a brief overview of Galileo's life, written by the English historian Mark Cartwright. I hope you liked it. Thank you so much. Practice math and stay curious. See you later. Bye bye.